Next, under coming attractions, is called enhanced weathering of minerals, or this is also referred to as accelerated weathering. I think everybody knows what weathering means. On the very long time scales, we look at the temperature anomalies of the Earth going from 500 million years ago. Let's say we start in the Cambrian. If you don't know the geologic time scales, don't worry about it. Solar system got formed 4.6 billion years ago, and Earth was in some primordial soup condition, and then it got these continents forming which have been moving forever, and then in the beginning there was no free oxygen in the atmosphere. Methane was probably the greenhouse gas. There are lots of issues about explaining these things because sun was also 30% less luminous, so energy coming in was less. We have to explain how the water remained in liquid form for sustaining life, but we know that life was found about 3.85 billion years ago, and then somewhere around 2.4 billion years ago enough photosynthesis began to happen in the water, and then maybe there was dissolved oxygen in the ocean. Eventually there was oxygen in the atmosphere at some percentage of the current level, which then increased to the current level. Photosynthesis and carbon uptake and oxygen release was a key part of this process. And so we have Hadean, which is the beginning where there was no life. It was called hell. And then Archean, where the beginning of life is discovered. And then we have Proterozoic, early life, and then Phanerozoic, which is visible life. And Cambrian is where the big explosion of species happened, and then Ordovician, Silurian, Devonian, Carboniferous, and so on. There's the times when photosynthesis became so abundant that the CO2 was drawn down and there was global coolings, snowball Earth episodes, and so on. But the main point is that as the temperature of the Earth has varied as much as 15 to 20 degrees warmer than the current period, going back to 500 million years ago and during the time of the dinosaurs, CO2 has always been a part of the story. And as the CO2 gets sequestered in the ocean, in plants, in on land, and so on, in wetlands and so on, weathering is a slow time scale regulation process of how CO2 dissolves in rain. It falls on land and rocks and organic matter. Most of it washes into the ocean, but there is a constant weathering of the minerals. Okay, so that's the story of CO2 and temperature over long times. They have been very closely tied with each other, and we are heading into the future now, which is what we are worried about. By 2100, how much warming will we reach, and what are the scenarios of CO2 emissions which will make this happen? So this is another way to look at it. If we start here in about 2010, if we do nothing, no climate policies, then this is the range of warming we would get by 2100, 4.1 to 4.8 degrees centigrade, which would get us way back into somewhere here. And the problem is that if the world has been so warm before, why do we worry? Well, because we haven't experienced anything like that. If we imagine that modern human beings, like agricultural and then now technology people, have basically evolved through this Holocene, which is a very stable period, and we've been around, of course, for a couple of million years in terms of our ancestors, but still the range of temperature change experienced is rather mild compared to what this would get us, all this glacier melting, sea level rise, and so on. Current policies will get us down here, and pledges and targets under the Paris Agreement would bring us down a little bit. But if we want to meet targets like 2 degrees C by 2100 with 66% probability, or the much safer 1.5 degree pathways, then we basically have to reduce carbon emissions, annual greenhouse gas emissions along these pathways. So action should have already started, but we are not on these paths at all. So that means we need to find many ways of drawing down carbons, more carbon than we emit. We're not going to stop emitting carbon anytime soon, so it's a matter of how much we take out compared to how much we emit. That's generally broadly referred to as geoengineering, where either you are going to reduce solar radiation by the euphemistically called solar radiation management, where you put reflectors in the atmosphere, in the stratosphere, and so on. You put dust and so on. But that wouldn't reduce the emissions and the CO2 in the system. Whereas enhanced weathering is a way where you actually use a natural process like weathering to draw down CO2 and have some co-benefits. So that's the main idea. How would you do it? There are layered ultramafic olivine rocks. This is from Duke Island, Alaska, which can be ground up and spread on land in agricultural lands and so on. If they're ground up, then their weathering rate goes up by a lot compared to rain falling on the rocks and slowly weathering it, or what is called biologically enhanced weathering, where lichen, moss, and plants and so on grow on the rocks, crack them open, and release pieces of the rock, which also enhance weathering essentially. Now, some experiments have been done. This is from a paper that argues for enhanced weathering on agricultural lands, which would solve food security problem as well as wash off into the ocean and slow down the acidification of the ocean. So right now, increased CO2 in the atmosphere is acidifying the ocean, which means corals and other calcifying animals cannot survive. They cannot calcify. Acidification of water makes them melt or not be able to build the coral reefs or the skeletons they need. So this is saying enhanced crop vigor and yield due to greater uptake of silica, calcium, potassium, and micronutrients. So this is enhanced root growth due to improved pH, nutrient supply, and physical conditions. So if you go around and spray silica and other dust from ground up rocks, you would accomplish these things. So they are thinking of applying basalt or mill ash from sugarcane mills, which also contain potassium and other nutrients. So that's silicate rock weathering, which is good because it takes two CO2 molecules, one of which gets re-released during the weathering. You can see here. So it sequesters one molecule of CO2. Okay, so weathering products in surface and groundwater runoff, less nitrogen, higher silica to nitrogen ratio. I'm kind of rushing through these because these are concepts that have been tried. There are lots of questions still to be answered. Okay, nonetheless, that would enhance ocean alkalinity and growth of diatoms, foraminifera, and corals, which are calcifying and silica shell forming animals, which are critical for ocean acidification controls. So argument is that it is possible to accomplish these things. The further schematic here says, here is global change, increased net uptake of CO2 and decreased emission of N2O, which is another high global warming potential greenhouse gas, can be accomplished with enhanced weathering. That would slow down ocean acidification and associated impacts on corals and fisheries. The Great Barrier Reef, for example, is having tremendous impact of warming and acidification. Bleaching because of warming mostly, but also acidification. And this would also enhance global food security by reduced use of finite high-grade rock for phosphorus and potassium fertilizers, decreased soil nutrient loss, erosion, and sea level rise, crop production and protection, increasing food supply, and eventually population growth and dietary changes more than doubling food demand by 2100 as projected can be better dealt with in terms of enhancing food security through these methods. But if you just do the calculations of, let's say, 1 ton of olivine is required to draw down 1 ton of CO2, then you would need billions of tons of rock to be sprayed. How to ground it up, how to transport it, how to spray it, is it really using less energy than the CO2 it would actually draw down? or will it mostly go into compensating carbon emissions by all these processes? So here is a truck spraying the ground up rock, for example. Theoretically, yes, this is fantastic idea. This is also proposed for the ocean. So here is rock being sprayed, enhanced weathering being driven, and that's going to drive mineral dissolution of products into coastal waters and oceans eventually, doing ocean alkalinity enhancement and giving us enhanced marine production, and also you can directly dump mineral dissolution products into the ocean. For example, dissolved iron in regions where iron is a deficient nutrient in the ocean has been tried in what is called iron fertilization to enhance phytoplankton photosynthesis. So the question is, how big a part of the solution will these be? Will these work? That's the question. They are being tried. They are being argued that they are feasible, but no experiment has been done on scale large enough to actually draw down sufficient CO2. So that's the real test. How much can we accomplish with this method? But as a coming attraction, it is an exciting idea to think about, right?